3 in the morning. The room is dark, the clock says something you did not want to see, and you are completely, uselessly awake. You are not sick. You went to bed at a reasonable hour. You slept well enough until about 2, and then something shifted, and now the ceiling is there and the night is there, and your body has no interest in returning to sleep no matter how still you lie. This happens to most people over 50, not occasionally, regularly, and the explanation you are most often given is that you simply need less sleep now. That is part of the answer. It is the smaller part. The larger part involves 2 systems crossing in the dark on a precise schedule, and a piece of brain tissue in the front of your skull that has been quietly losing its ability to generate the deepest kind of sleep for years. Those 2 things together explain why the ceiling is there. Let me take them in order. The folk wisdom that older people need less sleep is not wrong. It is incomplete. Jan Duffy and her colleagues at Harvard's Brigham and Women's Hospital ran a study in 2009 that examined exactly this question. They took older and younger adults through 26 hours without sleep and measured how each group handled the deprivation. The older adults did better. They had fewer attentional lapses, 4.86 per hour of testing compared to 10.34 for the young adults. 0% of the older group fell asleep involuntarily during the waking period. 58% of the younger group did. The older adults tolerated sleep loss more gracefully. But the same study measured what their sleep looked like at baseline before the deprivation, and this is the part the folk wisdom leaves out. The older adults woke roughly 30 times a night compared to 4 times for the young. Their sleep efficiency, the fraction of time in bed actually spent asleep, was 82% against 93% for the younger group. The hardware was fragmenting visibly every night. The fragmentation just was not producing the kind of immediate daytime collapse that makes people seek help. So the honest version is this: healthy older adults do seem to need somewhat less sleep, and they handle disruption with more resilience than the young. And they are also losing, gradually and structurally, the machinery for making the deepest kind of sleep. Both are true. The folk wisdom tends to use the first fact to wave away the second. What I want to spend time on is the second. Sleep is not a single thing. It is not a uniform darkness the brain enters each night and leaves 8 hours later. It has architecture. There are stages, and they are not equal. The 2 main families are REM sleep, the stage associated with dreaming and emotional processing, and NREM sleep, which runs in 3 levels from light to very deep. The deepest level is called slow wave sleep, named for what appears on an EEG when you observe it. The electrical activity of the brain at this stage is slow and large, waves rolling at less than 1 cycle per second, with amplitudes that can reach 100 microvolts or more. Big, long, sweeping oscillations that look almost nothing like the fast, flickering activity of waking or dreaming. These slow waves are not simply a sign that the brain has gone quiet. They are generated on purpose by specific tissue doing specific work. Memory consolidation, metabolic clearing, the restoration of certain cellular processes all appear to be concentrated here. And after 50, they start to disappear. Matthew Walker, Bryce Mander, and Joseph Weiner published a review of sleep and human aging in the journal Neuron in 2017 that draws together what decades of EEG work has established. One number from that review stopped me. Slow wave activity in the prefrontal cortex, the front part of the brain just behind the forehead, is reduced by roughly 75 to 80% in older adults compared to young adults. Not 10%, not a quarter, 3/4. And the reduction concentrates in the region of the brain that thins most visibly with normal aging. The medial prefrontal cortex is the tissue that generates these slow waves. It is also the tissue that undergoes the most marked atrophy over the decades. Mander and colleagues found that the severity of that atrophy directly predicts the severity of the slow-wave impairment. The tissue that generates the waves is the tissue that is shrinking. The thinning and the lighter sleep are not two problems arriving from different directions. They are one problem in one place. Sleep spindles go alongside the slow waves. Spindles are fast, brief bursts of electrical activity, roughly 11 to 16 cycles per second, each lasting a second or two, most frequent during NREM sleep. They are thought to be central to the consolidation of memory during the night, stitching the day's experience into more stable form while you sleep. After 50, the spindles thin. By some measures, their power falls by half, most sharply over the frontal regions of the brain and most dramatically in the later cycles of the night, in the hours before dawn. So the deep architecture of sleep is changing. Now the clock is shifting too. The suprachiasmatic nucleus is a cluster of about 20,000 neurons sitting at the base of the brain, roughly the size of a grain of rice, that coordinates the timing of sleep, body temperature, hormone release, and dozens of other daily rhythms. It is the master clock. And with age, it changes in two ways that matter for sleep. A review of the aging circadian clock published in the Journal of Clinical Investigation in 2017 found that the melatonin rhythm advances by 1 to 2 hours in people in their 60s and beyond compared to their 20s and 30s. The whole clock runs earlier. Sleepiness arrives in the evening. Morning waking arrives before dawn. But the rhythm does not only shift, it flattens. The amplitude of the melatonin signal dampens. The wake-sleep transitions become less abrupt, less well-defined. The clock is not only earlier, it is quieter. This is why many people over 60 feel a genuine biological sleepiness by 8 in the evening that they did not feel at 40. The clock moved, and it is why they wake at 5 regardless of when they went to bed, regardless of how long they planned to sleep. The clock does not only push the edge of the night forward, it pushes morning forward with it, and it does so with less authority than it once had. Now put the two pictures together, because this is where the 3 in the morning ceiling stare gets its full explanation. Sleep is governed by two interacting processes in the model Alexander Borbely proposed in 1982, and researchers have been refining ever since. Process S is homeostatic sleep pressure, the accumulation of adenosine and related compounds during waking that creates the drive to sleep. It builds all day, peaks at bedtime, and then drains during sleep, fastest in the first hours of the night when slow-wave sleep is heaviest. By midnight or 1 in the morning, a large fraction of your sleep pressure has discharged. By 3, it has drained steeply. Process C is the circadian wake signal, the internal alarm that begins climbing toward dawn. In a healthy young adult, the circadian wake signal is still low enough at 3 in the morning that the remaining sleep pressure can hold sleep together. The two processes balance at the right moment. In an older adult with a phase-advanced clock, the wake signal has already moved an hour or two forward. It is climbing earlier, and the deep, slow-wave machinery that discharged most of the homeostatic pressure in the early night is weaker than it once was, so less pressure remains to counteract the rising signal. The crossing point, where sleep pressure can no longer hold back the circadian wake alarm, arrives earlier and more abruptly than it did at 30. 3 in the morning is not an arbitrary hour. It is approximately where two systems meet in an aged, phase-advanced clock. The ceiling stare is not a symptom, it is a schedule, two processes crossing at their weakest point, on time. There is one counterintuitive detail in this picture that inverts what you might expect. Adenosine, the main chemical of sleep pressure, builds during waking and binds to receptors in the brain to create the felt drive to sleep. The obvious assumption is that older adults carry less adenosine, which is why they feel less sleep pressure. But the Neuron Review notes that older brains appear to carry more adenosine, not less. The pressure may be higher, not lower. What has degraded is the receiver. Adenosine receptors, particularly A1 receptors distributed across the cortex, the thalamus, and the hippocampus, thin with age. The chemical arrives and finds fewer sites to bind. The pressure is present. The antenna that registers it has worn. The problem is not that the body stops trying to sleep. It is that the machinery for translating that signal into slow waves has weakened. The question that follows is what slow-wave sleep is actually doing that matters enough to warrant a dedicated, anatomically specific generating system. Part of the answer involves the brain's own overnight cleaning. The glymphatic system is a network of channels that run alongside the blood vessels in the brain and through which cerebrospinal fluid pulses during sleep. During deep NREM sleep specifically, the spaces between neurons expand by roughly 60%, allowing fluid to move through brain tissue far more freely than during waking. Metabolic waste products move with it, including amyloid beta, the protein that accumulates in the plaques of Alzheimer's disease. I want to be precise about where this science is. The glymphatic discovery is real. The link between slow-wave sleep and expanded interstitial clearance is documented. Maiken Nedergaard and her colleagues at the University of Rochester have produced striking findings here, and the work is young. Much of it was established first in rodents. Human evidence is only now building, and the causal direction is not settled. I will not tell you that losing deep sleep causes dementia. That is not what the research has established, and the arrow may run in multiple directions. What can be said is that the stage most directly implicated in overnight metabolic clearance is the stage that declines most sharply with age. What that connection means remains one of the more important open questions in sleep science. One finding from the Neuron Review is specific enough to stand on its own. The decline in slow-wave sleep is strongly sex-dependent, and the gap is not small. Men over 70 show roughly a threefold deficit in slow-wave sleep compared with age-matched women. Women retain deep sleep significantly longer and lose it more slowly. The underlying mechanism appears to involve the loss of VIP neurons, vasoactive intestinal peptide neurons, in the suprachiasmatic nucleus itself. Men lose more of the clock neurons that sustain rhythmic output, and the pattern of clock neuron loss maps onto the pattern of slow-wave sleep loss. The sex difference in sleep architecture is, in part, a sex difference in the aging of the clock. Before I close, one distinction matters, and popular writing consistently blurs it. Most of what I have described, the phase advance, the slow wave thinning, the increased fragmentation, the pre-dawn waking, is the normal architecture of an aging sleep system. It is not disease, it is structural change in a healthy brain, and understanding it as such is part of what I think is worth taking from this research. What is not normal aging is sleep apnea, which affects a significant fraction of adults over 60 and is frequently undiagnosed. Loud snoring, observed pauses in breathing during sleep, waking with headaches, or severe daytime sleepiness that no amount of sleep resolves are not slow-wave decline. They are a separate and treatable condition. The two can coexist. One can mask the other. Making the distinction requires a clinician. I mention it only because it is worth knowing that the category of sleep got harder after 50 contains more than one thing, and not all of them are architecture. 3 a.m, the clock says something you did not want to see. 2 processes crossed in the dark while you slept. 1 draining, 1 climbing. They met at the weakest point, in the small hours, in a clock that runs a little earlier than it did at 30, generating slow waves from tissue that has quietly thinned over the decades. The machinery is not broken, it is older and it runs differently than it once did. That is the whole story, or most of it. The ceiling is there, the night is there, and both are, in their way, on schedule.